First one is by Robert. He's going to be telling us about
All right, thank you so much. My name is Robert. For this talk, I'll be telling you guys about foundations for learning from noisy quantum experiments. This is a joint work with Steve Flammia and John Preskill. So one of the important questions in order to develop useful quantum technology is to understand what we can learn from quantum experiments. Here in this work, we will build a mathematical theory that's built on this classical learning, this wide literature on classical learning theory to study this question. The outline of today's talk, I would start by providing a formalism, and then I would dive into talking about two viewpoints, learning the intrinsic description and predicting extrinsic behaviors. Let's begin with the first part. So here in this work, we consider a classical agent, which is an abstract model for scientists, classical machines, etc., that can interact with a physical system that's operating quantum mechanically. The classical agent can conduct experiments and obtain experimental data from the physical system in order to learn about the physical system. Here we define one experiment as follows. So in one experiment, the classical agent will specify a sequence of action, denoted here by x, y1 to yl, followed by z. So each of them corresponds to this action space, Catholic x, y, and z. The instruction for one experiment is being fed into the physical system, and the physical system will perform a sequence of physical operation based on the action specified by the classical agent. So an intuition underlying this is the following. So imagine yourself as an experimentalist, you're a classical agent. You create some quantum device, that's the physical system, that you can play around with. So you can specify some knobs, such as like the pulse sequence you wanted to apply, or a certain kind of initialization process, or a certain kind of measurements. So that's being encoded in these actions, x, y, and z. So what the physical system would do is, depending on what x is, it would prepare a state rho x. So rho x is the quantum state that represents the initial quantum many-body system. That depends on this x. Then, depending on y1, we will evolve the physical system under the evolution, which is given by the CPT map E of y1, and then y2, and so on. So after this evolution, the physical system will be in some potentially highly entangled state, represented by this format shown on the top. And depending on what the action z is, the physical system will perform a POVM measurement, denoted as mz, to collapse the state and obtains a measurement outcome that's fed back into the classical agent. So that's going to be our definition for what one experiment looks like. Essentially, the classical agent specifies the instruction, the physical system runs this instruction under some physical operation, and it's being fed back to the classical agent. So what we're going to consider is that the classical agent might not really know what's being applied in the physical system. When it says do x, maybe the physical system prepare rho x, or maybe rho prime x, and so on. The classical agent can conduct multiple experiments based on previous experimental outcome. You can start with some instruction, get the measurement outcome, do a different set of experiment by specifying a different instruction, get the measurement outcome, and repeat. So after this multiple rounds of interaction, the key question we would like to understand is, what can the classical agent learn about the physical system? Could it learn, for example, given an action x, what is rho x? Could you learn, given action z, what is mz? Or could you learn to predict, given a new set of experiments, what the experimental outcome is going to be? So that's a key question we would like to understand in this work. In order to better understand this question, we need to make a few more definitions. The first definition is what we call the world model. Basically, a world model specifies the interaction between the classical agent and the physical system. That is, given all of these actions, x, y, and z, what is the actual physical operation, rho x, ey, and mz? So world model, this W is just this tuple that maps these actions to the physical operations. The classical agent and the physical system will live in some true world model that might be unknown to the classical agent. So the classical agent doesn't know what that is, but it might have a set of candidate world models. And in practice, this set is typically uncountably large. And that is what we call the model class, using terminology from classical learning theory. So this set Q is just a set containing all possible candidate world models, including the true world model. The classical agent knows that it's belonging to one of the world model inside this class, but it doesn't really know which one it is. So that's going to be the formalism that we're going to work with. Now, in the second part, we're going to dive into one common viewpoint, what we call learning intrinsic description. Here, the goal of the classical agent is that given some true world model inside this set of candidate Q, the classical agent is asked to learn all the physical operations in the true world model. That is, given X, what is rho X? Given Y, what is EY? And given Z, what is MC? The key question we would like to understand here in this viewpoint is whether it's possible for the classical agent to learn all of these physical operations if it doesn't know any of them a priori. To answer this question, we proved the following theorem. This is just a short statement of it. Basically, we showed that classical agent can learn any world model with unknown actions that allows it to explore the entire quantum Hilbert space and perform a POVM measurement that is not useless. So here, what we mean by useless is that, what we mean by useless is that when you perform this measurement, it always outputs the same random distribution independent of what state you're being measured on. So that's a useless measurement if you have such a measurement. If you only have such measurement, you're not going to learn anything. So as long as you have one non-useless measurement and you have actions that can exploit the full quantum Hilbert space, then you can actually learn everything, even though you don't have any idea what each of them are. So more precisely, the full theorem statement is as follows. Suppose you are given a model class, which is an uncountably large model class, that contains every world model W that has an unknown actions that prepares an unknown pure state, some unknown actions that form a universal set of unknown unitaries, and unknown actions that performs a POVM that's non-trivial. Then for any true world model inside this huge model class, all the physical operations in the world model can be learned. So now, in order to illustrate how the learning process works, I would like to show the proof sketch for this theorem. So for that, let's imagine we are the classical agent. So on our table, we have all these different actions, x1 to x6, y1 to y6, and z1 to z6. Each of them correspond to some physical operations that we don't know. So let's say we say perform x1, it prepares some state rho x1, but we don't know what that is. We say evolve under y1, and then we have zy1, which we also don't know what it is. And then finally, we do measure. Now what we'd like to show is that we can actually learn all of them. The first step, what we're going to do is what we call a unitary test. Basically, by performing experiments and using the fact that unitary is the only reversible process, it is possible to identify the actions that correspond to implementing a unitary. However, so for example, we identified that the unitaries are y2, y3, and y5. We don't know what they are, but after this identification, in step 2, we can randomly compose them. Essentially, what we do is we randomly compose these unknown unitary, and basically, using results about simply connected Lie algebra, one could prove that by this random composition, we will actually implement a random unitary that's being sampled approximately from unitary 2 design. Note that here, we still have no knowledge about what this composed evolution is. We don't know, after all of these composition, what is this, but we know that it's being sampled from the HAR approximately from unitary 2 design, which is approximately HAR up to second moment. So now we have this HAR sampler. In the third step, we're going to combine this HAR sampler and an unknown POVM MZ2, for example, to estimate state overlap. Basically, what we do here is we randomly sample an evolution that's from a 2 design, evolve rho x2, and measure MZ2. We do the same for rho x3 and measure MZ3. We then repeat this experiment for different random evolution. Now, what we can prove is that without knowing any one of these things, we don't know what rho x is, we don't know what E1 is, we don't know what MZ is. The experimental data actually enables us to estimate the expectation value, the inner product between rho x2 and rho x3. So this is using some interesting property about 2 design, and the novel thing here is that you actually don't really know what this POVM is, and you can still estimate the overlap. So now after having this overlap estimator that estimates the overlap between any 2 states, in step 4, what we could do is we can compose the different physical operation. We can compose the different state and the evolution to form all kinds of state. And what we are going to do here is we're going to identify a special set of states with a special geometry. The geometry is shown to this very long list on the right. Basically, you want that for some pair of the state, it will be equal to 0. For some pair, it's 1. For some of them, it's 1/2. For some of them, it's 1/3. And for some of them, it's 2/3. Basically, this special set of geometry allows us to prove that the special set of states we found has a very specific form. Basically, there will be a subset consisting of the bases, and then some consisting of the superposition of 2 states, 2 bases, and the superposition of 3 bases. The superposition of 3 bases is very important in order to translate relative phase information among the other states. So after this step 4, we will have this set of special states and an overlap estimator, which allows us to perform quantum state tomography to learn all the state, to perform quantum process tomography to learn all the processes, and to perform quantum POVM tomography to learn all the measurements. So together, one could see that by starting from knowing nothing, the classical agent could gradually do experiments to build up its knowledge about what property does these operation that it's constructing has. And basically, what we can prove is that, essentially what we show is that without knowing what any physical operation is a priori, through experiments, the classical agent can learn all physical operations, as long as the actions allows it to explore the full quantum Hilbert space. So now after talking about this sort of very abstract theorem, let's look at some case study. So the first question we would like to see is what can be learned under the same assumption as randomized benchmarking. So randomized benchmarking is a very famous tool for learning average gate fidelity. So it's a single value that allows us to characterize how noisy our Clifford gates are. Typically in randomized benchmarking, one assumes that the Clifford gates are subject to gate independent noise. That means that for every different gates, the noise process is the same. So this is a very common assumption. When this assumption is highly validated, previous work has shown that randomized benchmarking could fail miserably. So here we're going to make the same assumption as randomized benchmarking. However, we show the following. We show that not only can you learn the average gate fidelity, which is done in randomized benchmarking, you can actually learn all physical operations, including what is the noise on the Clifford gates, what is your initial state, what is the measurement, what is the noise on a different non-Clifford gates like some T gates, what is the noise, or what is this arbitrary CPT map, what is this arbitrary state, etc. However, you can only learn it up to a single unlearnable parameter. That is the fidelity of the noisy all-zero state. One can prove that no matter what experiments you do, you will never figure out the fidelity of the all-zero state. So in a sense, you can just set it into 1 since you cannot learn it. Previously, there have some work that focus on a special case that is for how to learn the noise channel on the Clifford gates under this assumption. So there have been several developments, many of which was actually QIP's previous talk. One of the best protocol known today is by Hsin et al. On estimating gate set properties from random sequences. Basically, they utilize some very smart way of running the randomized benchmarking and analyzing the data from randomized benchmarking in order to learn the noise channel on the Clifford gates. Here, the algorithm we propose not only learns all physical operation, but in particular, for learning the noise channel on the Clifford gates, we can prove that the number of experiments actually scales linearly in the number of parameters of the object we're trying to learn, which is quadratically fewer than this best-known randomized benchmarking-based algorithm that was published last year. So in case study 2, we would like to see when would gate noise becomes unlearnable. So here we identify a very, very simple system. Consider you have a qubit system where you can perform a perfect initial state. You can perform a perfect basis measurement. However, when you perform Clifford or T gates, they will be subject to a small Pauli noise. So Pauli noise is essentially this incoherent noise that is with some probability you have X error, Y error, or Z error. So here we consider the setting where you only have Pauli noise, which can be done approximately through Pauli toroid. However, this Pauli noise could depend on the gate. So for a different Clifford gate, this Pauli noise could be different. And what we prove is that actually no benchmarking protocol can learn the true Pauli noise in this setting. So one might ask, what about this very powerful ACES technique that Steve Flammia proposed last year? So basically ACES is a method for learning gate-dependent Pauli noise for Clifford gates. So basically the theorem also applies to that. However, the resolution there is that ACES assume one could perform perfect stabilizer state. However, here we only assume that one could prepare a perfect initial state 0. So if you wanted to prepare, say, plus, you need to apply a Clifford gate onto 0. And then this plus state would be noisy. So that's sort of how one could circumvent any contradiction with results known in the literature. So that concludes the second part of the talk. In the third part, I will briefly talk about predicting extrinsic behaviors. So here, the key idea is that instead of learning the true physical description, which as we've shown in case study 2, can sometimes be impossible, the classical agent is tasked to learn an effective model for predicting experimental outcome. That is, we don't care if the classical agent is accurately learning the physical description of rho X, E, Y, and MZ. All we care about is the classical agent is learning some effective model, which can be non-physical, maybe some neural network or some other kind of methods, such that given a new experiment given a new sequence of action, X, Y1 to YL, and Z, the classical agent can predict the distribution of the output. So the plus side, the positive side of such a viewpoint is that you would never encounter this unlearnability results. It's always learnable because you can just run old experiments and then just gather the data. So in a sense, you can learn all of them. You're not really predicting new experiments though. However, the downside is that it's much weaker than learning intrinsic description. So it depends on the use case. Suppose that you wanted to learn intrinsic description because you wanted to identify where my device goes wrong. Is this state going wrong? Is that gate doing bad? Is that measurement bad? You want to learn intrinsic description. However, for predicting extrinsic behavior, you would not necessarily learn that. For predicting extrinsic behavior, it's useful when you wanted to use the quantum device, such as you wanted to do some error mitigation, you wanted to do some error correction, and so on. So in this work, we proved the following. We showed that actually in the worst case, classical agent cannot do better than simply running all experiments, which is kind of surprising. You have to really run all experiments in order to predict all experiments. However, which is also kind of bad news. However, we showed that given a mild assumption, that is, you're given some states and POVM elements that could linearly span the quantum state space, then we proved that the classical agent can use an exponentially fewer experiments to learn to predict all experiments. Oh, actually, and this exponential speed up in L is achieved using a rigorous learning algorithm that builds on ideas in gate-set tomography. So actually, one way to think of gate-set tomography is that it's learning an effective model for predicting extrinsic behaviors. So to conclude, in this work, we developed a mathematical theory for understanding what we can learn from noisy quantum experiments. In many settings, learning is indeed possible and prediction can be efficient. However, I do want to emphasize that our understanding of the situation is still far from complete. We don't really have a good way of saying that given a model class, is it learnable? Given a model class, can we have an efficient algorithm for learning it, etc. So I think that would be a very important future research question. So in order to build more intuition in our paper, we also provide more examples of unlearnable systems. We also establish quantum advantage in using devices and using quantum devices, noisy quantum devices, in the learning task that was recently implemented on Google's Sycamore processor. And actually, Jordan Kotler would talk a bit more on this advantage. And in the subsequent work, we will propose a mathematical framework that allows us to develop rigorous neural network algorithm for learning a wide range of noisy quantum systems. That's it for my talk. Thank you so much for listening.
So, if you can think about any practical implications of these, they were really sort of intuitive to one like that practical experience.
Yeah, could you say anything about, let's say, practical implications of the results you presented?
Yeah, sure. So for this theorem, I think it's just telling us that as long as we have all the actions that allows us to explore quantum Hilbert space, we can in principle learn everything. So I think it's a nice positive result. It doesn't tell us how efficient we can be in this theorem, but it does tell us that there's hope in learning everything, like what all these states are that happens in our physical world. In particular, the theorem on the gate-independent noise also showcased that by making some common assumption that people use in benchmarking literature, maybe we can learn much more than what people have already studied. And yeah, and this one tells us that actually there are cases where things are unlearnable. So one should be careful not to fall into there, and one should try to understand what are systems that's actually unlearnable and how to avoid such scenarios.
Hi, so I wanted to ask about a detail of your theorem, which you I think didn't include. Do you characterize learnability in terms of a combinatorial dimension of your model class? Or
yeah. So that's actually something I was imagining for building better understanding. Like, could we characterize the efficiency, but here's a weird thing, like. Usually in classical learning theory, it would not be unlearnable in a strong sense like what's happening here. So understanding what this unlearnable means in terms of maybe some combinatorial kind of measure, I think is very interesting. So, but yeah, but at the moment, not quite.
All right, thanks. I think it's interesting too.
Thank you.
Hi, thanks for the great talk. I was wondering, so how does your results relate to things like self-testing, if you know about that area?
Yeah, so I've talked to Ma about this. I think there are some relations. So some of the approaches that we're taking in the theorem seems to be able to suggest some results about like some rigidity of underlying things and so on. I haven't worked on self-testing so much, but I do see there are connections there. So
yeah, because in self-testing, usually you have you need two spatially separated devices, but in your case, it seems there's a single device.
Yes, it's a single device, and we're trying to learn it.
Which seems to be a stronger than your results seem to be subsume some of the self-testing results.
I wouldn't say so, because there are some. Okay, so the theorem statement here is that. Okay, so when we talk about learning intrinsic description, what I mean is the ability to learn all the physical operation up to a global unitary and anti-unitary transformation. I think there have some ways of dealing with that in self-testing, which is quite different in the way I'm dealing with it here. So yeah, I wouldn't say it just subsumes that, but I think there are definitely some interesting connections.
Okay, thank you.
The two.
What does it mean to learn something? So I guess is there a question of how accurately you can know something? Because I guess you have this like no-go, right? Where you say that you can't learn something.
Yeah, that's a great question. That's a great question. So in this theorem, when we say we can learn something, it means that we can learn for each of these operations to arbitrarily high accuracy when we increase the number of experiments we perform. So as we increase this, we can get better and better understanding of what that is. We can really pinpoint that.
I see.
And for this unlearnable results here, basically what we mean is that basically you just cannot learn what that small poly noise is.
But is there some sense in which you can almost learn it?
That's a great question. So actually there will be a bound. There will be a lower bound. It's like a noise floor, and then you cannot learn beyond that noise floor.
I see.
You can learn up to that noise floor, but then there's like a regime where you just you cannot fully identify what that poly noise is.
So you have your channel and you have some error bars on the description of your channel, and those error bars can never be made arbitrarily small.
Yeah, like if you even do infinite number of experiments, that error bar is just that.
I see. Okay, that's clear. Thanks.
Thank you.
Wait, well, it's not that.